Are there ways in which phosphine might be a useful molecule for extraterrestrial life in a way that terrestrial life hasn't harnessed it? So I guess maybe we could start, though you've touched on it a bit, with just the ways in which terrestrial life. So I think there are these worms, maybe by hydrothermic vents, that make use of phosphine, but how explicitly it's used on Earth. And because I saw so interesting thoughts you had about how aliens might use it.
So on Earth, we still don't know why life makes phosphine. We know that it does, but it's just robust circumstantial evidence, which is true actually for most molecules we consider biological molecules. It's much easier to, kind of watch a biological kind of small petri dish with some biology on it and then watch what molecules it produces. It's much easier to say, oh, it produced those molecules than it is to figure out what is the enzymatic pathway, like what is the actual chemical mechanism that made it. And so this is not surprising, but I think for some people it's like, wait, you don't even know why they're making phosphine? Maybe they're not making phosphine. Maybe it was just there. And that's not true. So we do know. But why is an incredible question, because it is really, really, really hard to make. And so the best explanation we've got is that there are other molecules that are really, really hard to make, that the universe doesn't just spontaneously make easily, like isoprene, for example. And these molecules, do I have isoprene? I do, wait. And isoprene is
These models are handy.
A much more fun model than phosphine. Look at this, come on. Isoprene, deceptively simple because it's only carbons and hydrogen, but you can see it's more complex, is produced by trees at an enormous cost, a sacrifice, which is the theme here. The universe doesn't sacrifice, but life does. And when life on Earth makes molecules at a huge cost, when it sacrifices energy to make these molecules, it's usually for a pretty complex behavior. In the case of isoprene is to signal. So trees use it to signal to each other danger. And it gets destroyed very quickly and creates a blue haze. It's why the Rockies are blue, why you see a blue haze in the mountains. That's isoprene being destroyed. But the reason this makes sense is if you're trying to communicate with a molecule, you don't want to make a molecule that could accidentally be there already, because then your communication is flawed. And so you're willing to sacrifice, to put in the work to make a molecule that could be a clear form of communication. So that's the case of isoprene, and that could be the case for phosphine as well. Phosphorus is also a limiting nutrient for life. So a lot of life puts a lot of work into getting phosphorus compounds. And so people have suggested that it could be part of like a bartering economy in the oceans, which is really cool, but a theory with a lot of problems. But the most obvious way in which life is willing to sacrifice to produce something really weird is because it's a good weapon. And so we already know phosphine kills. So it could be very well that anaerobic life is willing to make phosphine to protect itself from the oxygen-loving attacks of life that we like and smells nice. And so defense, attack, communication, or some economy are good explanations for why you would want to make phosphine, but we still don't know why.
So on Earth, at least, just to summarize a little bit. So on Earth, at least, so far as we know, phosphine could just be a byproduct like oxygen and photosynthesis, not necessarily be useful, rather than something that's produced and used like ATP or isoprene. But phosphine may be functional like isoprene. And
it kind of has to be functional because it's costly. So byproducts are not costly. Byproducts are usually an easy way to get rid of something. No one's going to sweat out phosphine for fun. It's expensive to make. And so molecules that require a sacrifice are usually involved with complex things rather than byproducts of other interesting actions. And that's kind of why it's also a good sign of life, because other molecules like water or methane, lovely molecules, definitely produced biologically in large quantities. So they're biosignatures in that sense. But they're produced in 1,000 other ways on a terrestrial planet or a habitable moon. It's not hard to make methane. And so life makes it and not life makes it. With phosphine, very little not life will put in the work to make it.